All right, ladies and gentlemen, now is our turn. We are Department of Industrial Informatics. In the reported period, we had a little bit less papers accepted. This time it was like 8 journal papers in Q1 or D1 journals, but they are, I think, of very good quality. If I should say one name, then I should speak about Mohamed Rohaninejad, which is our postdoctoral researcher. He has contributed to 4 of these papers, and I think nearly all of them are in D1, which is, I think, very good direction. It's in industrial informatics and scheduling area. And if you will go down to these topics, you will find that we have published in 7 different journals. So the outreach is relatively wide. We are not just in one niche sub-community, but our research, which is basically in scheduling, is reaching different, let's say, communities from theory down to industrial papers. We have also a new member, which is Chrpa. He will present today as well. And he has published 2 papers at for a conference, which is kind of unusual to us. So as you might know, we have several industrial partners, typically Škoda, Porsche, and Eaton. And this time we have got also some contract from ČEZ, famous Czech energy company, and Continental. The project from ČEZ was acquired by Tonda Novák, and it was about profit optimization in energy production. And the one by Continental was acquired and led by Šůcha, which is our classical topic in energy-efficient robotic production. As far as for awards, Pepa Grus got Best Student Paper Award at the Cross Conference. He will speak today about the same topic. In methodology 17+, we have got grade 2 for, I think, very nice application result, which was food activated opening of the 5th door using machine learning while processing signals from different ultrasonic sensors. And a bit unusual result is award for Pavlína Koutenská, which was a diploma student supervised by Zdeněk Šůcha, and she ranked the 2nd in IT Spy. IT Spy is a student project of the year. There were like 1,200 submissions, and she got the 2nd place with her diploma thesis, surgery planning using branch in price algorithm, which was enhanced by machine learning. Okay, so on the last news, you might know about it. We have got a RoboProx project with the help of many of you in this room. And the project will run till June 2028 and has very famous names in advisory board. I would just to name, for example, Jan Karel Lenstra, which is like Nestor in combinatorial optimization, or Toshio Fukuda, which is former IEEE president, and Wolfgang Walster, Nestor of Industry 4.0, or Mike Pinedo, which is, I think, the leading researcher in scheduling. So these are demanding people, so our teams will have, I think, very hard times, and we will need to work better and more efficiently. You see that the teams are coming from different faculties, in fact, 5 different faculties of CTU and 2 research institutes. A big part of the budget goes to CERC and Faculty of Electrical Engineering. And beside of that, we have also Technical University in Ostrava, Brno Technical University, and University in Pilsen. The work is split into 2 work packages. One is led by Professor Babuška on robotics and informatics, and another one is led by Milan Korda from Faculty of Electrical Engineering on control systems and materials. Okay, and that's it from my side. And I would like to invite Josef Grus to to present the first paper, which is, I think, here. Okay. Okay, the floor is yours.
Hello, my name is Grus, and I would like to present to you our application result called Automatic Placer for Analog Circuits. This work was initiated by ST Microelectronics company, who also provided us with both the input data and the understanding of the problematics. I will start with short motivation behind this work. So the process of placement is a process when engineers need to determine the positions and orientations of devices, such as transistors and resistors, given the input circuit schematic. One such example is shown in the figure. And just to know, this problem is essentially an extension of 2D rectangle packing, and is quite similar to floor planning. To obtain a high quality placement is crucial for the overall physical design of the integrated circuits, due to the fact that it simplifies the subsequent step of routing of elements. It leads to circuits with small area and lower power consumption, which increases the competitiveness of the products. In case of digital integrated circuits, this was already quite automated, mainly due to the fact that digital devices are standardized. They all share the same height, which makes the problem quite low. On the other hand, analog circuits are still mostly placed manually. And the reasons are the different non-uniform sizes of the devices, different voltage levels, and complex proximity constraints that we need to adhere to. Just to note, even today, the analog circuits are still crucial for our work. They are found in many amplifiers, oscillators, and other devices. And according to our industry partner, ST Microelectronics, they still perform the placement step for these analog integrated circuits manually. It's a very time-consuming, error-prone process that requires hours of work, even for the circuits with less components, and it's highly affects the time to market. So there is quite a place for automate this process. Now I would like to speak briefly about the problem definition from more formal way. So our task is to place these devices, which are modeled as rectangles. In the figure, they are shown as the darker rectangles inside the colored boxes. And we need not only to place singular devices or rectangles, but also so-called topological structures. These are groups of devices that need to be placed in a regular pattern for the circuit to function properly. One such example is shown in the top right corner in the orange box. There are 2 rows of these devices. And we could also place them, for example, in 3 rows, 4 rows, and so on. These are different variants of the same topological structure that we need to consider in the optimization to achieve the best result overall. Given this, we also need to adhere to other constraints. One such example are different minimum L distances between rectangles. Each device is actually surrounded by a pocket. This is essentially an empty space that is there for technological reasons. It is shown as this colored box around the device in the figure. And we need to make sure that these pockets are sufficiently distant from each other, depending on the different voltage levels and so on. However, given special circumstances, we can actually overlap these pockets, as is shown in the top right corner as well, which leads to a much more compact design and more competitive product. Other constraints that were present are, for example, symmetry groups. This is shown in the bottom part, where there is a group of rectangles that need to be placed in such a way that they all have the same axis of symmetry. And our objective was to minimize 2 parts of criteria. First one was minimization of the mentioned area, and the second one was minimization of approximate connectivity to help with the following step of routing. Now, about optimization approaches, we started with integer linear programming, or started by graph drawing. This approach was sufficient for us to solve provided industrial examples. I don't talk about computer. And this was the first step of our investigation. Afterwards, we used meta-heuristics, namely genetic algorithms and covariance matrix adaptation, which would make our approach more applicable to larger instances, synthetically generated. Just in the figure, we actually show visualization of how the genetic algorithm searches the space of all different solutions. And finally, as a synthesis of heuristic approach and mathematical programming, we also tinkered with map heuristics. This gets us to the results of our application. We were provided 17 real-life industrial examples by the estimate analytics company. These were accompanied by manual designs, so we could compare them. And the experts from the company also provided us with verification of our results and evaluation. Just to note, while the manual designs required out of work each, we ran our approach only, or our solver only for 8 minutes per each example. So this would provide quite significant improvement regards the time is needed for the placement to be found. From these 17 examples, for 12 instances, we found a solution that was better in both the area and connectivity, given our selected metrics. Numerically, area was smaller by 10% on average, and connectivity was smaller by 13%. One such example of this comparison is shown in the figures below. The first figure shows how engineers see their manual design using their tool. The second is our visualization of the same manual design, and the third one is our found placement, which we can see has areas quite significantly smaller than the manual one. Afterwards, we run further experiments on synthetic generated instances where we created instances with much more rectangles, 200 plus, so we could investigate other approaches I have already mentioned. So this gets us to the end of my presentation. So just to conclude, the estimate analytics company already bought our license to investigate its solution to placement of analog integrated circuits. We were also awarded the student paper award at CACORR 2023 conference. And currently, our full scope paper is after major revision in Q1 Journal of Computers and Operations Research. This concludes my presentation. I thank you very much for your attention. And just to note, if anyone else and if any other researcher is interested in similar problems of packing, cutting, or floor planning, we would love to hear from you, so we could be inspired in our further endeavors. Thank you very much.
So do you have any guarantees of optimality, or this is all hard to get?
For the small instances, that few of the instances were quite small. For them, we guarantee the optimality given our metrics or criterion, but for the larger one, we do not have these guarantees provided by the IoT solver.
Mohammed is disciplined.
Good morning. My name is Šůcha. I have the second part in this block. I will speak about work that concerns acceleration of combinatorial algorithms, which is a topic we are addressing for some time already, and resulted to some interesting journal papers. The first one was use of some classifier for accelerating a meta-heuristic algorithm. Second one, which was acceleration for branch and price algorithm for a North rostering problem, where we used some online machine learning approach to speed it up this algorithm. Third one I'm going to talk about, and the last one also concerns the branch and price algorithm, where we applied some ranking machine learning. And as Zdeněk already mentioned, our coder, Alina Koutecká, won the second place in the IID SPY competition out of 1,200 participants. The problem we are addressing in the paper is a simple scheduling problem, which is given by a set of jobs, and each job has only two parameters: its duration of the job, so how long it takes, and the due date, so when it should be completed. And obviously, the aim is to construct a schedule, so basically meaning a sequence of such boxes. And we want to find a good schedule, which is expressed in terms of tardiness. Tardiness of job means how much we exceed the due date. If we manage to complete the job before the due date, penalty is 0. If we exceed the due date by 1 unit, penalty is 1. If by 2, penalty is 2. So the overall aim is to find a schedule where we minimize the total tardiness, meaning sum of tardiness for all the jobs. So the problem is NP hard, and even though it's fundamental problem in scheduling, it corresponds to many practical problems in production planning. When we think about using machine learning to tackle combinatorial problems, we usually try to avoid end-to-end approaches, which are direct application of machine learning to that, which is quite frequent in current state-of-the-art literature. A good example is traveling salesman problem, which is frequently addressed by many researchers, but so far I have not saw a result that would be competitive with CACORR, which is a standard combinatorial approach, 20 years old, able to solve instances with 50,000 places to optimize. So therefore, we try to combine the fundamental properties of the problem with advantages of machine learning, and specifically for this scheduling problem, we went for Lawler's decomposition, which I will just simply illustrate on an example. Imagine an instance which is described in the table in the top right corner. So we have 4 jobs, each row for a job. Second column is for the duration, DJ, and DJ is the deadline. So the jobs are already sorted according to the due dates, which is a natural way how to order them, but of course there is no guarantee for the optimality. And the Lawler's decomposition is saying, find a splitting job, which is the job with the largest duration, and there is an optimal solution where the job, which is the red one, the splitting job, is on the 2nd position, 3rd one, or the 4th one in the schedule. And then according to the sorting, we assume we can split the jobs to the jobs that are before the splitting job and to the jobs that are after, and then they can be solved independently, which is quite strong property of the problem. In like classical combinatorial optimization, this problem or this decomposition is used such that they use branch and bound, so they explore all the combinations. And when we wanted to apply machine learning, our idea was this position can be guessed by the machine learning. We are happy with a heuristic approach, so it's quite straightforward. But designing a network that produces the position can be still hard for current machine learning techniques. So we have chosen a different approach, which was for every possible position of the splitting job, we estimated the objective function of the problem. So we take the jobs that precede the position of the splitting job, and for that we constructed the machine learning, which is able to predict the total tardiness for those jobs. For splitting job, it's easy to compute that contribution, and for the successors, we did the same. Of course, even for that, the machine learning is not that easy because we need to handle varying size of instances. It's changing. Of course, combinatorial problems are difficult to approximate with machine learning, and there is a standard issue with the training data. So, without going into details, I want to say that after many experiments, the best results were obtained with recurrent neural network based on LSTM. And there were many tricks we had to apply to achieve good approximation. One of them, we were not directly estimating the objective function, but instead of that, we just estimated the deviation from some relaxed solution. And there were many tricks related to the generation of the training data to make it efficient and obtain a good results. We compared our solution with an exact approach where we limited the CPU time, and also with a state-of-the-art heuristic approach. So the comparison with the exact approach is on the left. So here we compare with a branching bound algorithm where the time was limited to 50 seconds, and the comparison is done in terms of the CPU time as well as the optimality gap. And you can see for the instances larger than 300 jobs, we already get a faster CPU time and much smaller optimality gap. For the state-of-the-art heuristic, which was a genetic algorithm, our algorithm is even on 50 jobs much faster, and the optimality gap was much better. To conclude, our vision for design of such algorithm is to really combine fundamental properties of such problems with advantages of neural networks. We managed to come up with an efficient way to generate the training data instances. Results are really nice. We did state-of-the-art approaches, and a nice property of the neural network we designed is that it really is able to generalize the acquired information, because training was done on instances with up to 100 nodes, but the experiments were carried out on instances up to 800 jobs, and the results were still great. This research resulted in a publication in European Journal of Operational Research, and currently we carry on with this topic in cooperation with the team led by Mikuláš. Thank you for your attention. Any questions?
So how can you improve on an exact approach?
It's basically in terms of the CPU time. So we just want to speed up the exploration of the solution space.
So I understood that the gap there was like for your approach.
Our approach was a heuristic. So therefore,
There was time limit.
time limit. So when we compare with an exact approach, we need to define a time limit, but we also need to measure time and the quality. That's essential. And this is usually disregarded in the machine learning area, where people try to solve problems like DSP.
So the element perhaps on a CPU also.
Yeah, we dominate in CPU time and the optimality gap as well. Thank you.
Okay, cool. Good morning, everyone. So it's my pleasure to tell you something about comparing planning domain models. So to give you an idea, when we deal with what is called domain-dependent planning, so that one of the key elements that we need to develop is actually the model of environment and the model of action that the agent can take. So in our case, we basically use, which is well known and well studied in the planning community, we use strip semantic, where we are describing the environment by a set of first-order predicates. And planning operator have the precondition artifacts. All these are sets of predicates. Now, why do we need to actually compare domain models? Because if we have what is called knowledge engineering process, when we would like to develop some model, so which means that, for instance, in software engineering, also we are developing some algorithm, and from time to time, so we need some version control and somehow track changes what has happened. So we need kind of this tool. Also, there are on the market some automated domain acquisition technique that actually can learn from some data from some observation domain models, and we would like to evaluate them. So how, for example, different from original from each other. Of course, we would like to have some, assignments to give to students. So we would like to have some tool to check whether actually students work on their own and, didn't copy from themselves. And of course, we also have some competition. So the last edition was in 2016 of the ICCAPS competition, which is about knowledge engineering for planning and scheduling. And the last edition, and also there will be the edition this year, so will concern about the knowledge engineering process and domain development. And of course, such a tool for comparison can help us in evaluating the competitors. So now to give you an intuition of what we actually mean by comparing domain models. So that if you look at this example, so that we have two kind of simple logistics domain. In the first, on the left-hand side, so we have a truck that is delivering in packages from one location to another. On the right-hand side, we have a shuttle that is delivering passengers from one location to another, right? And so that you can get an intuition that actually these models are structurally the same. So the only thing what is different is the name of operators and name of predicates, because we have slightly, let's say, different object, but structurally the model is the same. So that give us a definition would be called strong equivalence. So that this was some idea which was started by one PhD student in Huddersfield some time ago, but then it didn't work well at that time. But we kind of resurrected the idea last year, a year before last year, and came with definition of strong equivalence. So the thing is that we would like to capture that the domain models are structurally identical, but what might be different is the naming of the components like predicate and operators. So the thing is that what we would like to find are basically two reactive mappings that map the names of predicates and names of operators respectively. And of course, so that we have to make sure that basically, so if we do some mapping, that for instance, the structure of the operators will be the same, so that it will still have the same precondition, delete, and other effects. Now, we would like to represent domains in some graph ways, because one of the results which I will summarize just in the next slide is to kind of use the notion of isomorphism to actually prove strong equivalence. And to do this, so that we need to model domain models as graph. And we simply represent predicates and operator named by vertices. And we have three types of edges that are connecting these operators with predicates, depending whether the predicate is in operator's precondition, delete, or other effect. So, and this is one of the main results that we say that if the domain models are strongly equivalent, if and only if their respective lifted domain model graphs are isomorphic. But we can go further, because of course strong equivalence is basically something saying, okay, models are strongly equivalent or not. But for the diff tool, so we need a bit more. So that we again took an inspiration from graph theory and with the notion of what is called graph edit distance. So that this is the, let's say, minimum number of changes we have to do to the models we are comparing to make them strongly equivalent. So which means that in the context of planning, so that if we add a vertex, so that we are adding some predicate, or if we are adding a type of edge, we are adding precondition, delete, or other effects to the operator. And of course, we can also add operators as well, which is again a vertex. Now, so now basically the task is to get some, not only to decide whether these graphs are isomorphic, but to kind of calculate what is graph edit distance and to track what actually how the models have to be changed to simply get the understanding what are the ASA differences. So for that, we used answer set programming, where we defined the program like this with 8 rules. And basically, these rules are actually about, calculating that, graph edit distance. So to make sure that we are, mapping the nodes that are kind of a part of that, strongly equivalent part, and that we are adding vertices of edges such that we are optimizing for the minimum number of changes in the models to make them strongly equivalent. So now also we introduce some pre-processing rule, which actually help us to simply compute the solutions more quickly. And just in short, basically a pre-processing deal with some sort of invariants like, for instance, if we have predicates with, let's say, different number of arguments, so they can't, be mapped to each other, and similarly for operators. So because to make them equivalent, they have to have the same number of arguments. So and now when we get the ASP solution, so that we have just some simple algorithm to translate it into human readable form, so that we just translate the changes into something that we are adding some vertex, or we are adding some edge which has some label like that. This is a precondition for that and that operator. So now we made a comparison in the sense that we took some models from the international planning competitions, and we did just a few changes to see basically how the tool will work. So you can see just from the table that without pre-processing, so that it didn't work very well, because basically the ASP program generated quite a lot of rules, and simply for slightly let's say larger models, so it didn't work. But with pre-processing, so that we were able to get the results very quickly in a half second. Now we also compared RPG domain model, which is actually a task which was in the knowledge engineering competition in 2016, and we just took two models developed by two different teams. And we realized that there are quite differences, even though they were modeling the same domain. And then just to kind of check the scalability of our approach, so we also compared different domain models to each other, just the last two rows. And in that case, we were, let's say, not able to find all optimal solution, but at least one, so that and we made it within 1 second, which is good, because it means that despite that there is some computational complexity, because graph edit distance is NP hard, so that in practice that the tool can be used. So just to quickly conclude, so that we define the concept of similarity domain model, which is based on the notion of strong equivalence, so that we use the graph theory to somehow model the domain model, the models, and to just use the notion of graph edit distance to actually identify what are the differences between two domain models. So as we have shown that experiments show that the tool is applicable in practice, and in hopefully near future we are planning to extend it to more expressive formalism such as temporal planning or BDDL plus. And okay, that's it. So any questions?
Okay, so the last speaker from our department is Mohammad Rohaninejad.
Hello everyone, my name is Mohammed. Today is my pleasure to present one of our research titled An Integrated Lot Sizing and Scheduling in the Reconfigurable Manufacturing System under Workforce Constraints. As the title indicates, we are facing a problem with three pillars: reconfigurable manufacturing system, lot sizing and scheduling problem, and workforce availability constraint. In the following, I will explain particularly each of these pillars in detail. What is reconfigurable manufacturing system? After emergence of dedicated manufacturing line, companies were able to produce one specific core product at high volume and low price. Dedicated manufacturing line is a cost-effective system, but as long as demand exceeds the supply, I mean, as long as they can operate at their full capacity, But by increasing the pressure from global competition and also customization, there may be a situation in which they cannot operate at their full capacity. So by increasing the change to the customer demand and also popularity of individualized product, flexible manufacturing system has been introduced where companies are able to produce high variety of the product. Generally, we know it with CNC machine. You know, the CNC machine are very expensive to purchase and set up. And since they are designed for high variety of product, generally they will put all of the available functionality and flexibility. Even in some cases, it doesn't require it. The logic behind of it is, okay, buy it just in case you maybe need it one day. So generally, in flexible manufacturing system, a big portion of our investment is wasted because it's out of production. So reconfigurable manufacturing system is a new paradigm of manufacturing to fill the gap between the DML and also FMS. In the reconfigurable manufacturing system, we can adjust the system functionality and also the system capacity in a time and cost-efficient manner. Reconfiguration can be implemented in the system level, for example, by adding or removing the machine, or even adjust the layout of the machine, or can be implemented in the machine level by add, remove, or adjust some module of the machine. I'm talking about some kind of modular machine that is exactly subject of our study. Okay, what is lot sizing problem? Lot sizing problem is one of the main challenging problems in the production planning, aiming to plan multiple items during the planning horizon, consisting of finite production period. This problem answers three main questions: which item should be produced, in which periods, and how much or how many, to fulfill the demand and also minimize the total system cost as objective function. Also, there is a main constraint in this problem. We name it material balance constraint. This constraint guarantees the material flow in higher planning horizon. So in the classical lot size, we establish this constraint between the start and finish of each period. But in the simultaneous optimization of lot sizing and also scheduling that is subject of our research, we have to establish this constraint inside the period and also within a period. That this constraint leads to different situations between two consecutive operations in each period that you can see in this figure, and also makes the problem so complicated. The traditional way to handle this challenge is splitting some period to some micro period or some small time slot, and then establish this material balance constraint for each small time slot. That this is not very practical approach because computation is very expensive. In our research, for the first time, we developed new formulation for the problem to establish the material balance constraint inside the period without splitting the period to some micro period. That new formulation enables us to solve the problem with much larger dimension. And finally, about workforce availability constraint. Despite improving mechanization of the industry and also widespread emergence of robots in the manufacturing, still human resource is an inseparable part of manufacturing, and we have to consider it in production planning optimization, as we did in our research. In our research, we optimize assignment of the worker to the task according to their availability. I mean, cumulative consumption of worker in each skill category must be, at each moment, must be according to their availability at that moment. So, based on explanation provided so far, I can say in short, we investigated a very practical problem in industry, considering the RMS as a new paradigm in manufacturing, and also it's a very complicated problem. Generally, the lot sizing problem is the class of NP-hard problem. In the capacitated version of problem, even finding a feasible solution, I'm talking about feasible solution, not optimal solution, is NP complex. So to tackle this complexity, we develop an efficient solution approach based on logic vendors decomposition. Generally, we decompose our problem to one main problem and one sub-problem. In the master problem that we solve it by MIP formulation, we optimize the lot sizing and also the machine configuration. In the sub-problem that we solved it by constraint programming, because constraint programming was about 10 times faster MILP for solving the sub-problem. We optimize the schedule of the task according to the worker availability. Generally, in each iteration, first we solve the master problem for entire planning horizon, and then we solve the sub-problem period by period. If we could find a feasible schedule for one period, we move to the next period. If not, we generate a feasibility cut. And in the next iteration, we add the new generated cut to the master problem, looking to generate some new solutions, and we continue whole approach until we reach a feasible schedule for entire planning horizon. There are also a lot of technical detail for this algorithm, also about our feasibility cut, that is the strong and new feasibility cut. At the last slide, you can see a part of our experimental result that we compare a MILP model with our solution approach in two indicators. One, total system cost as objective function, another computational time. Also, the solid line are about the objective function or total system cost. As you can see, the MILP formulation couldn't solve more than 2/3 of instances according to our time limit, that was 1 hour. While our solution approach almost could solve all instances less than 1 hour. An important point is our average optimality gap was around 4%. That is very good optimality gap. And also I would like to ask you pay attention into 2 dashed line that show the computational time. Comparing the computational time also show us that our proposed approach is very fast and quick approach for solving the problem. Also, there are a lot of other indexes that have been measured in the computational result that you can check them in the original paper. And also the result of this paper is published in International Journal of Production Research as a Q1 and well-known journal in production planning. There is nothing more, and thank you for your attention.